Good morning. Today we are going to study about crystallographic point groups. Before moving to learn about crystallographic point groups, we are going to get a brief about what are crystals. What do you mean by crystal? Any solid having an essentially discrete diffraction diagram is said to be a crystal. Any solid having an essentially discrete diffraction diagram is said to be a crystal. And the crystals are anisotropic homogeneous solid. Homogeneous and anisotropic solids, and the homogeneity is on the scale of a small number of atoms, and such a repeating unit is called as a unit cell. And this ordered rearrangement consists of a large number of unit cells that fit together to fill the space that are defined by 3D vectors. These 3D vectors are called, or which form an array, is called a lattice. The crystalline state is characterized by a completely regularly arrangement of the lattice points. The systematic arrangement of atoms in a crystal lattice poses a restriction on the symmetry axis are present inside the axis. So each crystal, it possesses an external symmetry and an internal symmetry. Each of the crystal will possess an external symmetry and internal symmetry. And among this, external symmetry depends on the symmetry elements and the interfacial angles of crystal. External symmetry, it depends on the interfacial angles of the crystal, and the internal symmetry, it is determined by the arrangement of atoms in the lattice. So we can detailedly note about the external symmetry. External symmetry, it is determined by 10 symmetric elements. N is equal to 1, 2, 3, 4, 6, etc. That is rotation axis Cn, and N bar 1, 3, 4, 6, which is the improper axis of rotation. And here it is rotation followed by inversion. And in molecular symmetry, we are studying as improper axis of rotation as rotation followed by reflection. But here it is rotation followed by inversion, and it is known as the auto inversion. Or we can say that external symmetry, it contains only pure translations. Only translations. And they are expressed by using, it contains no translations. They are expressed using point groups. The external symmetry, we are represented by using point group. Okay, it contains no translations. Okay. Then for internal symmetry, as we discussed earlier, internal symmetry, it is determined by the atoms, arrangement of atoms inside the lattice. It is determined by the arrangement of atoms in the lattice. On the basis of arrangement of atoms, there can be only 14 space lattice, referred to as Breif's lattices, and they combine to give 230 space groups. Among these 230 space groups, 73 are non-translational and 157 have translational elements of symmetry. So now we can discuss about space groups with translational elements of symmetry. In order to design symmetry, we have to study two symmetry elements. The first one is screw axis and second one is glide reflection. So the screw axis, it is rotation followed by translation, or we can see that the translation is due to the occurring of rotation, or it is defined as an operation in which a point is rotated by 2 pi by n about an axis and also translated by some distance but parallel to that axis is called screw axis. That is, we are rotating along a particular degree and the translation will be parallel to that rotation. The second one is glide reflection. This is referred to a symmetry element called a glide plane. In three-dimensional, the glide plane contains the result of reflecting a point through a plane. That is, reflecting a point through a plane and translating the direction of same lattice vector. Reflection, and due to this reflection there will be a translation. The restriction of the translation is to 1/2 of the length erases, because the repetition of this operation have to bring the initial point into coincidence with an equivalent point. That is, the translation will be half of the reflection plane. and it is of three types. The first one is axial glide plane. That is, if the reflection is along axis, we can say that it is axial glide plane. And we know that there are three axes, x, y, z, and we are calling it as the A glide, B glide, and C glide. The second one is diagonal glide plane, and if the reflection is through a diagonal plane or diagonal line, we are calling it as the diagonal glide plane. And the last one is diamond glide plane. This is the intermediate space between the axial glide plane and the diagonal glide plane, and we are denoting it by A by 4 and B. The next one is Hermann symbols. That is, we are using these symbols to denote the point groups of a crystallographic point or a crystal. And it consists of two parts. That is, the first one is a capital letter which indicates the lattice type symbols. And the second part contains lowercase letters and numbers that indicates the crystallographic symmetry element and their spatial arrangements or orientation. The lattice type symbols used are P for primitive, I for body centered, H for hexagonal, R for rhombohedral, F for face centered, A for centered on face A, and B for centered on face B. So these are the capital letters or lattice types. Then the next one is 3 bar, 4 bar, 5 bar or N bar. This is rotation followed by inversion. Rotation followed by inversion, it is again the external symmetry. Rotation followed by inversion or auto-inversion. So it contains no translation axis. So the translation free symbols are itself 3 bar, 4 bar and 5 bar. Then next we are using A, B, C, N and D. It's reflection plus translation, or we can say that they are the glide planes. Which are they are the glide planes. A, B and C glide. As indicated, reflection plus translation. When we are removing translation, it contains only reflection. And the reflection, that is denoted by the letter M. And there is only one exception, that is for diagonal plane D. Reflection plus translation, we are denoting it with the letter N. So we can see that for the external symmetry, the symbol will be same as the space group. Translation free symbols will be same as that of the symbols. And for screw axis and glide planes, we are changing the translation. Okay. Then the next one is the conversion of Schoenfly symbol to Hermann symbols. That is, if the symbols are CS and S1, they are indicated by the letter M. That is, it contains only one axis, they are denoted by the letter M. And if it is C2H, C2H indicates rotation followed by reflection along the horizontal plane. So rotation, for rotation we are using the symbol 2, 3, 4, etc. And here the rotation is along 180 degrees, so we can represent 2. Then sigma h plane is present here. Sigma h, it is always perpendicular to the principal axis, so we are using the bar 2 bar M. The next one is D2. We are indicating it by 2, 2, 2. C2V, C2V. It contains rotation and reflection. Rotation and reflection. Rotation, it is indicated by 2. Then 2 sigma V's. 2 sigma V's. Sigma V, reflection plane. We are represented by M. So the plane is M, M2. For D2H, it is M, M, M. C3. Only rotation along 120 degrees, so we can see that 3. S6. S6. S6 means improper axis of rotation, and is denoted by O. We know that C2N, CN or S2N is the point group symbol. So we can say that this is same as C32. So it will be 3 bar. Then D3, it is written as 32. C3B, 3M. D3D, 3 bar M. C4, 4. S4, 4 bar. C4H, 4 by M. C6, 6. C3H, 6 bar. C6H, 6 bar M. D6, 6 to 2. C6 by 6 mm. D3H, 6 bar M2. D6H, 6 by M mm. T23, tetrahedral M3 or 432. Tetrahedral 4 bar 3M, octahedral M3M. Okay, that's all about the crystallographic point groups.